Hello, chemistry. This is Mrs. Ellsworth. Now, just a reminder that we've talked about the early atomic models and that the Greeks believed in 4 different elements, that they kind of over-debated the atomists. There's also air here, too, that you can't see, fire, water, and earth. Okay, and then Dalton's model in the about early 1800s, he believed that everything was made up of little round spheres. Okay, and that different atoms from different elements, that they had different size spheres, and that the ones that were the same elements looked identical. Now Thomson, he figured out that there were electrons, so that ruined Dalton's model. So we've got a change here because now we know that there are parts to an atom, as where he thought that this was the smallest piece of matter. Anyway, so now that we know that there's parts to an atom, that kind of moves forward with the plum pudding model of Thomson. And so now it's about 1900. We've talked about how that in the early 1900s that scientists were figuring out that electrons behave as waves and as particles. We always talk about particles, but they also behave like waves. So then in 1911, that's a kind of a crisis time during World War I, Ernest Rutherford and several scientists are working in England, and they do a gold foil experiment. The gold foil is a very, very thin piece of gold. In fact, when I've held it before for gold leafing, you can actually put it over your finger and you can see it mold to your fingerprint. So it is very, very thin. And he believed that what was going to happen was that he was going to shoot these alpha particles from this radioactive source, and they were all going to just go right through it. Okay? And so he figured that the atoms go right through it, but as you can see, some bounce back, some bounce straight back, and it really surprised him. And from this, he determined a couple of things. Okay, here's the gold foil right here, and here's the alpha particles. Some are deflecting, some are going straight through, and some are even coming back. It really surprised him. In fact, he said it was quite the most incredible event that ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So he was not expecting that at all, and he realized something, that there's small little dense nucleuses inside of atoms. There's also a lot of space in atoms. So in Thomson's model, okay, he just expected it all to go through because this positive mass in here, evidently they didn't think that was really hard, and that would just go through it. But they learned that, hey, this small dense nucleus is strong enough and solid enough to bounce back those alpha particles. So that debunked Thomson's theory, and now Rutherford's theory is saying that, hey, that there are small dense nucleuses and lots of space in atoms. But there's a problem. What about those electrons? They know that electrons exist already at this time. Thomson, discovered them, but they question, where are those electrons? Sometimes this guy, Rutherford, he is kind of given the word a planetary model. Sometimes that's a word used for Niels Bohr's atomic theory, but the whole thing is that they were working together. And 2 years later, Niels Bohr, he kind of nails it because he figures out some problems with this. Rutherford thinks, hey, maybe these are things just hanging out there, or maybe they're going around like a planetary model. They're tossing a couple of ideas. So here we go. Dalton's model, little round small spheres. Thomson discovers electrons, so they know there's parts to an atom. This is positive, that's negative, so it has a neutral charge. Rutherford, lots of space, small dense nucleus. Okay, and so he's working with Niels Bohr, here's Rutherford, and they're still curious about where are those electrons. They know so much about the electrons, but yet they don't. Now Niels Bohr, he realized that Rutherford's theory, that these electrons, once that you go and you energize them and give them some light, then they would go and they'd emit photons and they'd go right into the center. Okay, and so he knows that this doesn't work. And if you think about gravity, this having gravity and pulling in the electrons, and when they're orbiting like a solar system, that is going to fall right into the nucleus, and so matter would not exist. So he came up with very specific orbits. Okay, and this theory seemed to explain much of the experiments that scientists were conducting at the time. He believed that only 2 electrons went inside of the very first shell or orbit. Okay, the second one 8. Next one, there's actually another one right here that's got 8 again, and then 18, 18. And so this isn't the best model I see that I picked, but you get the idea that the elements had very specific electrons in each shell. Okay, so let's go and look at this, because he was able to prove some of this with science experiments. So when you go and remember, in class we had one of those tubes hooked up to electricity, and then it would emit light. Well, the hydrogen atom was pretty exciting. Now he was able to measure some things. So he had a tube of hydrogen, and he went and gave it some electricity, and then he could calculate what type of line spectra that it would have. So let's talk about that. So the ground state would be where the electron is when there is no electricity hooked up. Okay, and here is the first energy level, second energy level, and the third energy level. So it takes more energy to be in the higher energy levels. So what happened is that what happened is that he went and shot some electricity through the tube, okay? And when he shot that electricity through it, the electron hopped into the next energy level, okay? And so he shot some more electricity, and it hopped into the next one. It became in an excited state, and that's what they call it, excited state. And as that occurs, it pops right into the next one. Notice it did not stop in between. It popped right into it. Okay, then what happened is that the electricity was taken away for that second, and what happens is that it goes and it releases a photon. Notice when it releases a photon, it either goes down here or else it go down here. But notice that it does not stop in between. Now this is called a photon emission. Okay, and sometimes students they misunderstand that the grammar in here that's saying that light has been emitted. Photon emission, that's just a different form of the same word. Now notice that these are quantum leaps is what they call it, when it left from one energy level to the next. Okay, and because you don't go in between. Okay, these are discrete again, where you have to be in specific ones, and that's that. The electron does. So he was able then to calculate what the energy level would be for this. Okay, how much energy they put in it, how much strength of light came out, and at what wavelengths were they emitted at. And so he was able to measure that, and he calculated, and it fit up perfectly. So this is cool. He had math that would help support his atomic theory with the energy levels and the orbits, but it only worked for the hydrogen atom. So here, let's go ahead and talk about, this is what I just said. Okay, the theory with scientific equations, okay, is supporting the actual reading that he took with this line spectra from this test, the line spectra, okay, and that was emitted from hydrogen gas. This is great because the atomic theory was supported by math and actual evidence. Unfortunately, it only worked for the hydrogen atom. Once you went and stuck in more than one electron, it did not work. Okay. Also, Niels Bohr's theory was two-dimensional. It was flat. And of course, the Earth is three-dimensional. But this introduces quantum theory, and it is a simplified version, very simplified version of the newest theory, quantum theory. So, Bohr's model, what did he believe? He believed that the nucleus was made of protons and neutrons, just like Rutherford had discovered. Okay, electrons are in energy levels or orbits. Okay, the energy orbits have a specific number of electrons per energy level. It also shows the emission of light and how he was able to calculate that. So those are some common things that I found with Bohr's model. So now we're changing again. Solid sphere, smallest thing. Nope, there's smaller things, there's parts. Okay, and so the plum pudding model then gets changed into Rutherford's one that's got lots of space and a nucleus, and now Bohr's model. So that's pretty interesting because we've got specific orbits that the electrons can be in. Now the quantum model, what happened was that we know that there's a small dense nucleus. Rutherford proved that. Okay, and that contains protons and neutrons. Chadwick had found neutrons, and protons were given credit by Rutherford himself. Now Heisenberg, this is about right before World War II. In Heisenberg, they're still discussing those electrons because they know that Bohr's model is not perfect. Okay, and they want to know where exactly are those electrons. And Heisenberg said, hey, once you start looking into where an electron's location is, you became part of the experiment, so you've kind of shook it all up, and so now you're ruining it, and you can never see exactly where that electron is. Then Schrödinger, he goes and he figures out, this is where the big change is. You can't ever find the electron, but you can find a high probability of where that electron is located. Okay, and so these are now going to be called orbitals, as where orbitals, and that's where they have the highest probability of being located. Now the orbitals are very different shaped. Some orbitals are round, spherical. S orbitals are spherical. Some are peanut shaped, the p orbitals. They call that dumbbell shaped. Some are shaped like clovers, okay, and some are shaped like peanuts and rings. Okay, and the F orbitals are even crazier. So what happens here is that now with the new quantum theory, that with Schrödinger's equation, you can find a high probability of the location of electrons. Because if you're going to go and look for one, you're going to disturb it and you're going to become part of the experiment, and so you will ruin it. Now the electrons exist in orbitals. They're very different shaped, and orbitals are sometimes called electric clouds. And there are these 4 different shaped orbitals: spherical, peanut-shaped, clover-shaped, and freaky-shaped peanuts from several different planes. Okay, so what does it look like? Well, here's the 1s orbital. We've talked about electron configuration a little bit. Here is the 2s orbital. It'll contain 2 electrons in that one with opposite spins. Okay, here is the 2p orbital in one plane. Here is the 2p orbital in the second plane. Okay, and here is the 2p orbital in the third plane. Now we'll go into the 3s orbital. And so we get some electrons that are moving in very different shapes. They've got opposite spins that are entangled with two electrons are always entangled with one another, and they create this very unique looking quantum model. New quantum theory is so important for lasers, for reading your CDs, for lasers, for reading those barcodes. There's so many things that we use with communications. There's so many different ways that we use quantum theory that wouldn't be possible if we didn't understand how the electrons are moving within and outside of the atom. So here's that of quantum theory again. Okay, it changed over time. Dalton's solid spheres, smallest thing. Okay, there's actually pieces. So we have a plum pudding one with a positive mass and negative electrons. Okay, then Rutherford's gold foil experiment, he found that this is a lot of space, small dense nucleus. Okay, but those electrons are in very specific orbits or energy levels. And then we got the new modern atomic theory where we've got orbitals. And if you really think about it, the Bohr's model is not too far from this, because within this circle right here could have been 6 parts of the electrons plus a 2 in it, so that would hold 8 electrons. So really Bohr's model is kind of a really simple definition of what this one is. And the Bohr's model does help us understand quite a bit of the chemical compounds and how that they combine with one another. Anyway, I will see you tomorrow, and we will have some questions for you to answer about the new modern atomic theory called quantum theory.